Yeah, so in this video, let me try to motivate why it might be better to use a variational autoencoder instead of a regular autoencoder. And that is because in the variational autoencoder, because we force the latent space distribution to be a standard normal distribution, it will be easier to sample from that. So it will be better for generating new data using a variational autoencoder compared to a regular autoencoder. So let me introduce the problem step by step. So here is an overview of using a regular autoencoder for sampling. So the regular autoencoder that we encountered in the previous lecture. So what we did in the previous lecture was we took the MNIST dataset and then used the encoder to encode it into this two-dimensional latent space. Why did we use a two-dimensional latent space? Well, that was really arbitrary for my side here. I just wanted to have it two-dimensional so that I can visualize it in a scatter plot so that you get a feeling of how it looks like. But of course, the dimensionality is relatively arbitrary. I could have used a 3D, 4D, 5D, 100-dimensional latent space representation. But of course, then I wouldn't be able to make a 2D scatter plot. And as a rule of thumb, the larger your latent space is, usually you pick still something that is smaller than the input size, but the larger your latent space is, the easier it will be for the autoencoder to encode the information in the latent space and produce good reconstructions. Simply because you have you retain more information, or you have the ability to retain more information in this latent space. So at the end of the previous lecture, in one of the code examples, what I also did is, when we had this latent space, I was just looking at it and picking an arbitrary point. I think I picked something like, say, minus 2.5 here, and what's this, 2. So I picked a point, and then I put this through the decoder, and what came out was a handwritten digit. So one aspect about this two-dimensional space here in this autoencoder example is that it looks pretty crowded and kind of continuous in this region here. But this is really because we picked a two-dimensional space. If you have a very large dimensional space, maybe even like, 10 to 100, these points would be already very far apart from each other, and this wouldn't be a continuous space at all. So if you would just pick an arbitrary point in the higher dimensional space, it would be not really guaranteed that it produces a valid image that looks anything like the input data if you put it through the decoder. So just to highlight the issues with sampling from a regular autoencoder. So it's actually a challenge because regular autoencoders are difficult to sample from. The reason is that the distribution might be oddly shaped. So here actually it looks, to be honest, nicer than I expected, but there's no guarantee that it is anything like that, like organized like that. If you consider different data sets, or you may encounter that these are really weirdly shaped distributions, and weirdly shaped distributions make it really hard to sample from in a balanced way, right? So if you have a Gaussian distribution, you know how to sample from a Gaussian distribution, but if you have some arbitrary distribution here like that, you don't even know what this distribution is, right? I mean, how do you sample from that in a balanced way? It's kind of challenging. Also, the fact that the distribution is not centered at 0, 0 makes it also additionally harder. So here this distribution is just at some arbitrary location in some arbitrary fashion distributed. So it's really hard to sample from that in a way that we can generate valid data points. I mean, the regular autoencoder is still good for compressing data, but if you want to generate new data that looks similar to the training data but is new, that is usually not so good with a regular autoencoder. And the distribution is not necessarily continuous. And this is kind of hard to see here because it's only two-dimensional. But if we would imagine a higher dimensional space, everything would be pretty far apart from each other, and the distribution wouldn't be not continuous. Let's now consider the variational autoencoder. So we still have the same MNIST dataset, but now when we are training this variational autoencoder, the latent space will follow a standard multivariate Gaussian distribution. So here, just for example, I have only 2 dimensions, but of course, like for a regular autoencoder, the number of dimensions is arbitrary. So here, this is just the density function of the multivariate Gaussian. So also here for reference, but I bet you have already seen that before. And yeah, we now have, in this particular case, 2 dimensions. So according to that, the parameters are the mean vector and the covariance matrix here. So the mean vector with a mean for each dimension, and the covariance matrix with the variance for each dimension, the variances. And then here the covariances. However, we assume that the latent space, that the covariance matrix here is a diagonal matrix, so that it is, in particular case, an identity matrix, so there's no interaction between the features, or in simpler terms, the covariance matrix is an identity matrix like this, where we have 0 covariances and unit variance for each dimension, so the variance for each dimension is 1. Just a standard multivariate Gaussian distribution. Then, once we know this distribution, we can sample from this. So we can draw samples, and because this is a continuous distribution, we can expect that the decoder produces something reasonable when we sample from this distribution. So there are no gaps in this distribution. It's a continuous distribution. How do we sample from this? So here's how we draw a new sample Z. So we have standard deviation times epsilon plus the mean here. So actually we don't need to use the whole covariance for that, the covariance matrix, because the off diagonals are 0, like I showed you before. So we only need to store a vector for the variance, just to keep it simple. So this is just the variance vector, and these epsilons here, they are drawn from a normal distribution. So this is the way we sample. Why do we do that? I will go into this in more detail in the next video. It has something to do with the fact that we are still trying to train a neural network using backpropagation. And how do we backpropagate through our probability distribution? So I'll just give you maybe the short version now. Why not? Because what we do is we store this mean vector and this, let's say, variance vector. There is a little trick to that. I will explain that in the next video. But we store these 2 vectors here, and using those, so we can use backpropagation to parameterize these vectors, and then we use epsilon here during the forward pass to sample. It sounds maybe a little bit weird and abstract right now, but it will become more clear once I show you also the first code example. It will not be too far into the future, only finishing up this video. There will be a short next video, and I will show you the code example, and then I think this will become clear. So let me briefly talk about this logvar trick, which will be kind of important for implementing the sampling procedure. And then in the next video after that, there's one more on the loss function, but then I will actually show you how this works in PyTorch. And I think when you see the whole code, I bet it will make more sense why we want to store this mean vector and this variance vector, and also why we will use this logvar trick. All right, so stay tuned for the next video on the logvar trick.